Hello everyone, in this video we present a project involving the integration of a motor predictive maintenance system applied to an automated conveyor-based sorting system. The main objective is to improve system availability, reduce unexpected downtime, and optimize the performance of the motors used in the sorting process. The system consists of a conveyor that transports objects. Sensors detect the color of each object, and the system automatically directs them to the appropriate sorting area. Node-RED acts as our orchestrator. It receives uncommon messages, formats them, and simultaneously distributes them to our InfluxDB database for historical storage and to ROS2 for intelligent control. Thanks to Grafana, we have full visibility of the system. Here, we can see the historical data of the motor's humidity, temperature, and vibration levels. If any value exceeds a critical threshold, the system detects a potential degradation even before a failure occurs. Hardware architecture. The core of the system is an ESP8266 microcontroller selected for its integrated Wi-Fi connectivity and compatibility with IoT systems. It's connected to an U6050 vibration sensor, which detects mechanical imbalances, and to the HT11 temperature and humidity sensor to monitor the motor's environment. LED indicators are also integrated to locally display the system state, normal operation, warning, or critical condition. All sensors are installed directly on the conveyor motor to ensure that the collected data accurately reflect real operating condition.
The code is now uploaded, and the ESP82 begin transmission measures via MQTT. To process this data stream, we switch to our virtual environment running ROS2 JZ. This is where the integrations take place. We launch the Node-RED and Influx services, which acts as a bridge between the hardware and our monitoring interface. As shown, the virtual machine ensures pipeline stability, guaranteeing that no vibration or temperature data is lost during transmissions.
The data flow is managed by nodes RED. Raw measurements are converted, filtered, and securely transmitted. The central node distributes the information in two directions: historical storage and real-life robotic control. For analysis, we use InfluxDB as a time series database. The data is then visualized on a Grafana dashboard, allowing us to monitor humidity and vibration history. Configured alert threshold enable early failure detection as soon as anomalies appear in the graphs. The major innovation lies in the integration with ROS2 JZ. Motor health parameters are published as ROS topics: humidity data, temperature data, and vibration data. This allows maintenance data to be directly integrated into the sorting robot's control logic, enabling it to autonomously slow.
The system identified three operational states: nominal states, where all values remain within normal ranges; predictive states, when certain thresholds begin to be reached, indicative that maintenance should be scheduled; critical states, where the system triggers an alert and can initiate a safety shutdown to prevent further damage. The historical data also allows post-failure analysis, helping to continuously improve the maintenance strategy. In conclusion, this project demonstrates the effectiveness of IoT and data analytics in transition toward intelligent, proactive, and connected maintenance. Thank you for watching this video.